Okay. So let's return to our little simulation that we saw yesterday. And I want to make one more point about this. This has a frequency and it has a wavelength, and we learned yesterday that if we increase the frequency, the wavelength will go... What? We increase the frequency, the wavelength goes down. They're inverse, right? One goes up, the other goes down. And we didn't talk about energy. We need to talk about energy of a wave. And this is super, super easy. Let's look at the frequency here, okay? I want to... oh my, what's happening here? Let's reload this. No, there we go. Okay, so I want you to look at this wheel. See that wheel, how it's turning? That wheel is driving this piston up and down, making the wave. Look at the frequency. I'm going to turn the damping off. All right. So, whoa, I don't want any reflections. Oh, no. No end. There we go. There we go. Now we got what we want. So, there's our wheel. It's turning, making our frequency. I'm going to lower the frequency, and I want you to look at the wheel. And I want you to think about the energy. Look at the wheel right now. Think about the energy of the wheel. I'm going to turn the frequency down. What happened? Whoa. Turn the frequency down. What happened to the energy of that wheel? Slowed down, didn't it? So would that be higher energy or low energy? So when the frequency goes down, the energy also goes down. Does that make sense? And if we turn the energy back up, the frequency and the energy, so the energy and frequency, I don't know why my wheel keeps sticking. You saw it a minute ago. So when the frequency goes up, the energy goes up. So what does that mean about energy and wavelength? When the energy goes up, what happens to the wavelength? If the energy goes up, then the frequency goes up. And so what happens to the wavelength then? It goes down. So we have energy and frequency are directly related. They move together. One goes up, the other goes up. But energy and wavelength are inversely related. And so those are some general characteristics, some other things that we need to know about waves. I want to teach you a couple other relationships. First of all, the velocity of a wave is equal to the wavelength times the frequency. That's a formula. A formula for the speed. Speed and velocity we're going to use interchangeably. In physics we learned that they're slightly different, but we'll use them interchangeably here. So how fast the wave is moving is actually a product of the wavelength and the frequency. But that ends the general characteristics of waves, and now I would like to keep going and talk about one particular kind of wave, the kind of wave that we really care about a lot in this class and in this section. I want to talk about electromagnetic radiation, which you know is important because it's the title of your note sheet, and it's the very first vocab word. Electromagnetic radiation. There are a lot of ways to define electromagnetic radiation, but the simplest, easiest thing for you to remember about electromagnetic radiation is that it is a fancy way to say a one-syllable word that you've probably heard of. Does anyone know the one-syllable word that you've probably heard of that electromagnetic radiation is a fancy way to say? Light. There you go. She said light. Electromagnetic radiation is light. So today's entire discussion will deal with light. By the way, electromagnetic radiation is a mouthful. So when I say EMR, that's my abbreviated way of talking about electromagnetic radiation. Or I could just say light. Same thing. Now, as we talk about light, we're going to see that there are a whole lot of different kinds of light. lots and 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 lots of kinds of light. But before we talk about the different kinds, we should probably talk about what makes one kind of light different from another kind of light. We've all heard of without looking now, what are some kinds of light we've heard of? Ultraviolet is a kind of light, definitely. What else? Anyone else know another kind of light? X-rays. That's light. You already saw it a minute ago, did you? You didn't know that was light, did you? Oh, fancy. So, what other kinds of light? X-rays?
Gamma.
Gamma. Good. So, yeah, there are a lot of different kinds of light. And so we're going to do a little section about each one of them in a minute. But before we do, I want to kind of introduce generally this whole idea of all these different kinds of light. All these different kinds of light taken together are called a spectrum. Spectrum. You really need to first understand what a spectrum is. That's going to help us understand why one kind of light is different from another. As it turns out that all light, whether it be red light or gamma rays or X-rays or ultraviolet light or any kind of light, they're all the same thing. They're all these electromagnetic oscillations. It's kind of like electrons vibrating, is pretty much one way to think about light. And so they're all kind of the same thing, so we need to know what makes them different. Well, what makes them different is their wavelength or their frequency. Red light is different from blue light because it has a different frequency. Now, understand that frequency and wavelength are paired. They're kind of tied together. If we say they have different wavelengths, then we already know they have different frequencies. Because if we go back up here, the velocity of a wave is equal to the wavelength times the frequency. But there's one really important characteristic of light waves. This is not true of all waves. This isn't true of water waves or any other kind of waves, or sound waves. But light waves in particular have a very interesting property. They all go the same speed. Did you know that? All light waves go the same speed. Every light, whether it's red or orange or gamma or X-ray, travels at a speed of c, which is 3 times 10 to the 8th meters per second. But since 3 times 10 to the 8th meters per second is a lot to write down every time, we'll just write down c. It's a symbol that means a particular speed. And all light in a vacuum. We have to say in a vacuum because it turns out that whenever light travels through air or through diamond or through water, it actually slows down a tiny, tiny, tiny little bit. But that's not really that important for our purposes. 3 times 10 to the 8th, 300 million meters per second. Now it's important to get a good grasp of what that is. How fast is that? What could you do in a second if you were going 3 times 10 to the 8th meters per second? How far could you go? Would that get you around the Earth? Is the Earth got a circumference of 300 million meters? You probably don't know. Turns out that at that speed, you could go around the Earth like 6.5 times in 1 second. That's how fast light is. Light is really fast. And so, because they all, though, have the same speed, then we know that since they're all the same speed, since that number doesn't change, then for every kind of light, when the wavelength goes up, the frequency goes down, and so on and so forth. So if we return to our spectrum up here, we can talk about the spectrum, and what we have is we put all of the different kinds of light on the spectrum, and we arrange them from lowest frequency to highest frequency. That's how it's done on these papers. I'm going to give you one of these in a second. And on here it's always lowest frequency to highest frequency. You see there it says frequency increasing. Now you could like hold a mirror up to this and reflect it and have this on that side too, and that would be okay too. And some textbooks will do that. But I like it to go from increasing frequency. And so by virtue of that, you could just as easily say that the wavelength, if the frequency is getting bigger, then the wavelength as you go to the right must be getting smaller. And so what we're gonna do for the rest of the day is we're gonna kind of talk about each little section. We're gonna talk about radio, we're gonna talk about microwave, infrared, ultraviolet, X-rays, and gamma rays. But before we do that, one of the skills that you're going to be required to have on this test is you're going to have to know the order. You're going to have to know that it's radio, then microwave, then infrared, then visible, then ultraviolet, then X-rays, then gamma. You got to know that. So a couple of years ago, some of my classes helped me come up with a mnemonic, and it's ridiculous. It's a ridiculous mnemonic, but a mnemonic is like a sentence like my very eager mother just served us nachos. It's not 9 pizzas anymore, is it? It's nachos. rest in peace, pizzas. So the mnemonic is, in fact, radioactive monkeys increased the volume until the Xbox glowed. So the story you got to remember is you got a bunch of radioactive monkeys. They're like, hi, I'm a monkey, and I'm radioactive. So I'm sending off all these radioactive waves. And I'm playing the Xbox, as most monkeys do. But I can't hear. So I go up and I turn up the volume. And in turning up the volume, I'm getting close to the Xbox. And when I get close to the Xbox, I radiate it, and then it starts glowing. Got the story? Radioactive monkeys increased the volume until the Xbox glowed. Radioactive monkeys. Radioactive, radio waves, monkeys, microwave, increased, infrared. The volume is visible until, what's until? Until ultraviolet. The Xbox, that one's easy. X-rays. Glowed is gamma. So that's our mnemonic. That's gonna, if you can remember, it's a stupid sentence, but the stupider it is, the more stupid it is, the more likely it is that you're gonna remember it. Radioactive monkeys increase the volume until the Xbox glowed. Let's cut that one off there.